Hi, so this is part B video of section 5.2. So where we left off, we're ready to start talking about objective 3. So objective 3, we want to be able to determine trigonometric function values for special angles. So I have here just a couple of sentences. So the angles 30 degrees, 45 degrees, and 60 degrees come up often in examples and applications of trigonometry. So their trigonometric function values are of special interest. Therefore, we have two special right triangles referred to as 45, 45, 90, and 30, 60, 90 right triangles. Right. So these are two special right triangles that you want to be familiar with. Right. So the first one. Right, is the 45, 45, 90. Right, so these two degrees measure the same. Right, so one way to show that is by the dash through it. Right, so that's showing that those are the same. Right, or we could label it, that's 45 degrees and that's 45 degrees. Right, so one nice easy one to remember is the hypotenuse is 2, and the legs are square root of 2. Right, so you should definitely know this triangle. Right. Another thing that we can do is we can come up with a similar triangle. Right, so a similar triangle meaning that the degrees are the same. Right, so the shape's the same, but the sides are proportional to one another. Right, so essentially I could take this top triangle and multiply each side by a half, right? So what that would give me, so 2 times a half is 1, and then this would be radical 2 over radical 2, and this would be radical 2 over radical 2, right? So that's one possibility. And then another kind of version of this is maybe taking this same triangle, maybe multiplying all the sides by h, right? So essentially what you would have then is this would be h for hypotenuse, this would be radical 2 over 2 times h, and this would be radical 2 over 2 times h. Right, so those are just three different versions of the 45, 45, 90 degree triangle. Right, so I would definitely become familiar with these two I'm circling in red. Right, you should be comfortable with both of those, or at least one of those, right? Right. So then the other possibility is a 30, 60, 90 right triangle. So we can start out with like the same picture, and let's say this is 30 degrees, and this is 60 degrees, right? Then the hypotenuse is still 2, and then we're going to have a radical 3 and a 1 for the legs, right? So I think this is easy to remember because it's 1, 2, 3, and then just remember it's radical 3. And then I think this one is the easiest to remember also because it's all 2's, right? It's just that the legs are square root of 2, right? So also it's important to note that radical 3 is bigger than 1. Right? So since radical 3 is bigger than 1, that should go across from the bigger angle. So that's going to go across from the 60 degree angle. Right? So this would be radical 3, and this would be 1. Right? So I think, again, I think this triangle and this one are the easiest two to remember. Right? And then, if you want to get some alternate versions like we did here, we can get a similar triangle. Right, we can multiply times 2 again, or times a half, I guess. Sorry. Multiply all the sides by a half. So we get 1, 1/2, radical 3 over 2. Right? And then I could take that and multiply all the sides by h, right, to come up with h for the hypotenuse, 1/2 h for this leg, and radical 3 over 2 times h for this leg, right, where this is 30 degrees and this guy is 60 degrees. All right. So I can't stress enough, definitely know 45, 45, 90, 30, 60, 90 triangles. We're going to use it a whole bunch in the class, right? So then, I guess just a side note too is that this 45, 45, 90 triangle has a special name. It's called an isosceles right triangle, right? So isosceles means that you have two sides that, at least two sides that are the same, and it's also a right triangle, so it's an isosceles right triangle, right? And then also another kind of fact is if you're ever unsure about if you drew the triangle correctly, right, you should be able to apply the Pythagorean theorem, right? So in other words, to double check this, we would want to verify that radical 2 squared plus radical 2 squared does in fact equal 2 squared, right, which it does, right? It'd be 2 plus 2 equals 4, right, which is true. And then same thing here, you'd want to verify that radical 3 squared plus 1 squared equals 2 squared, which it does, right, to double check this guy and this guy, right? So that's just a nice little mental check, just to be sure you did it correctly. So now ready for example 3. So we want to evaluate cosecant of 45, secant of 45 degrees, and cotangent of 45 degrees, right? And something important to remember from section 5.1 is that if there's no degree symbol, like it doesn't say degrees, then it's understood as radians, right? So don't forget that. So having this degree symbol here is real important, right? So cosecant of just 45, right? That implies 45 radians, right? Which is huge, right? Because, 2 pi, so roughly, less than 7, so roughly 6 radians is a full rotation. So 45 degrees is much different than 45 radians, right? So they're not the same, right? So just keep that in mind, that degree symbol is real important, right? Or if you see like a homework problem where it just talks about an angle and doesn't say that it's in degrees, well, that's because it's in radians, right? So since we're dealing with 45 degrees, we want to start off by drawing the 45, 45, 90 right triangle. So this is 2, radical 2, radical 2, right? So then, let's just say that I'm, this is my angle I'm thinking of, so I'll just put theta here, right, just to remind us that's where we're focusing on, although it doesn't matter because both angles are the same, right? So if I want to find cosecant of 45 degrees, right, this would be equal to, remember that's the same thing as 1 over sine of 45 degrees, right? Well, if you remember SOHCAHTOA, sine is opposite over hypotenuse, right? So this would be equal to 1 divided by, so the opposite side would be radical 2 over 2. The hypotenuse is 2, right? So this gets me to, we'd have 1 times the reciprocal, which would just be 2 over radical 2, right? So just dividing those two fractions, right, we multiply by reciprocal. And then I need to rationalize the denominator, so I'd multiply top and bottom by radical 2 over radical 2. So this gives me 2 radical 2 all over 2, right, because radical 2 times radical 2 is 2. So the 2's we can divide top and bottom by 2, and we're left with just radical 2, right? So there's the final answer, right? So then secant of 45 degrees, right? So we can do this similarly, right? Secant of 45 degrees would be 1 divided by cosine of 45 degrees. Right? So this would be 1 divided by, so cosine is the adjacent, so that would be radical 2 over 2, right? So notice it's the same work as up here, right? So this is just going to equal radical 2, right? So we could go through the same steps, but we're going to get the same answer. It's the same exact work, right? These two parts match, right? So this is true from previous work. So then cotangent of 45 degrees is equal to 1 divided by tangent of 45 degrees, which would be equal 1 divided by, so using the TOA, right, that would be opposite, so radical 2 over the hypotenuse, or excuse me, over the adjacent, which would be radical 2. So radical 2 divided by radical 2 is just 1, right? So this would be equal to 1 divided by 1, which is just 1, right? So cotangent of 45 degrees is just 1. Right? So we got all three of those answers. So the next example, we're trying to find sine, cosine, and tangent of 30 degrees, right? So again, we want to draw special right triangle. So this time we need the 30, 60, 90 triangle. So remember, 2 is the hypotenuse, just like the 45, 45, 90. And then we have 1 and radical 3 left to place. So radical 3 goes across from the 60 degrees because it's bigger than 1. And 1's going to go across from 30. Right, so we're focusing in on the 30 degrees here, right? So sine of 30 degrees is equal to the opposite over the hypotenuse, right? From SOHCAHTOA. So this would be 1 over 2. Well, 1 half. Cosine of 30 degrees is equal to, so that would be the adjacent over the hypotenuse, which would be radical 3 over 2, which we don't have a radical in the denominator, so we don't have to worry about that. And then tangent of 30 degrees is equal to the opposite over the adjacent. So this would be 1 over radical 3. So I need to multiply both sides, or top and bottom, by radical 3 to rationalize the denominator, right? So here I'm just multiplying by 1, right? So that gives me radical 3 over 3. Right, so those are my 3 answers for this problem, right? So we're just getting comfortable with the trig functions and the special right triangles. Right. So then example 5, we have 2 parts and we're given some trigonometric expressions and we're asked to simplify the expressions, right? So what we want to do here is replace the values in for the trig functions and then simplify, right? So in other words, I want to know what's the cotangent of 60 degrees, right? So since the first one's dealing with 60, 30 degrees, we just need to draw that special right triangle. So here's 2. Let's say this is 30 degrees. This is 60 degrees. So this would be radical 3, and this is 1, right? So then, remember we have SOHCAHTOA. So cotangent is going to be, so cotangent of theta is going to be equal to the adjacent over the opposite, right? Because it's just the reciprocal of tangent, right? So tangent's opposite over adjacent, so cotangent is the opposite, right? So, so cotangent of 60 degrees is going to be equal to, so we're focusing in on here at 60 degrees. So the part that's adjacent would be 1, and the opposite would be radical 3. Right? And then cotangent of 30 degrees. So now we're focusing in on here, right? The green. So we want to go adjacent, which is radical 3, over the hypotenuse, which is 1. So this is just radical 3. Right? So filling this in, this would equal 1 over radical 3 minus radical 3 over 1. So we want to get common denominators. So what I could do first is rationalize the first denominator. So this would be 1 over radical 3 times radical 3 over radical 3. And we have minus radical 3 over 1, right? So all I did was multiply the first guy by 1, essentially, right? Because radical 3 divided by radical 3 is just 1. So I'm not changing the value. So this gives me radical 3 over 3, because radical 3 times radical 3 is just 3. And then we have minus radical 3 over 1. So now it makes it a little easier to get common denominator. So I can get a common denominator of 3. So I need to multiply the top and bottom by 3 of the second fraction. So this gives me radical 3 over 3 minus 3 radical 3 over 3. And then so now I can subtract. So we subtract the numerators. Keep the same denominator. So now what I'm thinking is, you can put a 1 in front of here if you'd wish. And you're just treating radical 3 kind of like a variable, right? So if you have one radical 3, you take away 3 of them, you get negative 2 radical 3 all over 3. Right? So then that's the solution, right, for that one. Right? So then similarly, we want to look at sine and cosine of pi over 3 and pi over 6. So it's important to remember that 60 degrees is equal to pi over 3, and 30 degrees is equal to pi over 6. Right? So the triangle is the same, right? And remember SOHCAHTOA, we can easily find sine of pi over 3 and so forth, right? So sine of pi over 3, so I'm just going to write the parts in. Sine of pi over 3 would be the opposite, so radical 3 over the hypotenuse, which is 2, right? And then we're multiplying that times cosine of pi over 6. So cosine of pi over 6, we would be focusing in here on the green angle. So that would be the adjacent, which is radical 3 over the hypotenuse, which is 2. And then I'd have plus. And then the cosine of pi over 3 would be, we're looking at the yellow angle now, right? And then the adjacent would be 1. Hypotenuse is 2, so this would be 1/2. And then sine of pi over 6, so we're focusing on the green 30-degree angle. So sine is opposite, which is 1, over the hypotenuse, which is 2, right? So then we just need to simplify this. So multiplying the first two fractions, I would get 3/4, right? We'd have radical 3 times radical 3, which is 3, and then 2 times 2, which is 4. And then this second part here, we take 1 times 1, we get 1, and 2 times 2, we get 4. So we got 3/4 plus 1/4, which equals 4/4, which is just 1. Right, so part B just equals 1. Right. All right, so now I want to fill in a table of reciprocal and quotient identities. So the first one, and we've looked at some of these. The last two rows we haven't looked at yet. So the first three are stuff that we've already done. So for example, understanding that cosecant of theta is equal to 1 over sine theta. So I've already introduced that. Or we can look at it as sine theta is equal to 1 over cosecant of theta, right? So in other words, sine of theta and cosecant of theta are reciprocals, right? Are multiplicative inverses. So then secant of theta is equal to 1 divided by cosine of theta, or cosine of theta equals 1 over secant of theta, right? So in other words, secant of theta and cosine of theta are reciprocals, right? So remember, the C's don't match, right? I presented that before. So the C's and S's don't match, right? So that's an easy way to remember those. And then another one that we know is that cotangent of theta equals 1 over tangent of theta, or we can say that tangent of theta equals 1 over cotangent of theta, right? So cotangent of theta and tangent of theta are reciprocals, right? So like I said, those are things that I've already introduced. So the next two things we need to look at are the quotient identities, right? So tangent of theta is equal to sine of theta divided by cosine theta. And cotangent of theta, right, which would be the reciprocal, would equal cosine of theta divided by sine theta. Right, so those are two new things that we haven't looked at. So in other words, what I could say is that tangent of theta is the ratio of sine theta and cosine theta. We could also say that cotangent theta is the ratio of cosine theta and sine theta. All right, so then next we have example 6. So we're given the sine of angle beta is equal to 3/7 and cosine of beta equals 2 radical 10 over 7. We want to use the reciprocal and quotient identities to find the values of the other trigonometric functions of beta, right? So essentially what we're kind of exploring is if I know sine and cosine of an angle, I can find the other 4 trigonometric functions values by using the material that we just presented in that table. So for example, if I want to figure out what tangent of beta is, remember that's equal to sine of beta divided by cosine of beta. So just plugging in these values, this would be equal to 3/7 divided by 2 radical 10 over 7. Right? So something I could do here to make this a little simpler is I could multiply the top and bottom by 7, and what would happen is these 7s would cancel out, so we end up with 3 divided by 2 radical 10. Right? And we don't like the radical 10 in the denominator, so I can multiply top and bottom by radical 10 over radical 10. So this would be 3 radical 10 in the numerator, and then this would be, 2 times radical 10 squared, right? So radical 10 squared, that's inverses of one another, right? So this part would just be equal to 10, right? So we'd have 3 radical 10 over 2 times 10, which is 20. Right? So 3 radical 10 over 20 is what tangent's equal to. And then we could easily find cotangent of beta And, you know, to be able to do this, we can just steal, you know, look at this part, like we did before, where we already found tangent with a radical in the denominator. So at that point, I could just pull this over here and then just flip it, right? So this would be 2 radical 10 over 3. And there's nothing further I need to do with that, right? So I didn't explicitly say this, but, you know, what I'm thinking about is that cotangent of beta is equal to 1 divided by tangent of beta, right? Because they're reciprocals. And then cosecant of beta is equal to 1 divided by sine of beta, which would be equal to 1 divided by 3/7, which would equal, you know, 1 times 7/3, which equals 7/3. Right? And then lastly, secant of beta is equal to 1 divided by cosine of beta, which is equal to 1 divided by 2 radical 10 over 7, which would be equal to 1 times 7 over 2 radical 10, right? Which is equal to 7 divided by 2 radical 10. And then I can multiply top and bottom by radical 10 and get 7 radical 10 over, so this would be 2 times 10, which is 20, right? So this part is similar to before, right? If I have 2 radical 10 times radical 10, you know, this part here is just 10. So this becomes 2 times 10, which is 20, right? So there's those 4 solutions. Right? All right. So then on the next page, I want to present what are called the Pythagorean identities. Right. So I want to show you where these come from, and then you'll see what the Pythagorean identities are. Right. So first thing to present these is, let's just draw a typical right triangle, right? I'm going to call this angle theta. I'm going to call this side A, this side B, and this side C, right? So sine of theta is equal to, it would be equal to the opposite, which would be A over the hypotenuse, which is C, right? And then also, if I want to find cosine of theta, this would be equal to the adjacent side, which is B, divided by the hypotenuse, which is C, right? So then a statement that I can get from this right triangle using the Pythagorean identity, right, which is a squared plus b squared equals c squared, right? And that's why these are called the Pythagorean identities, because they're identities that come from the Pythagorean theorem, right? So basically, we're going to get 3 different identities, and how we're going to get these is we're going to make each of these parts, right? So there's 1, 2, 3 parts. We're just kind of play around, and let's make one of them equal to 1, right? So for example, let's maybe think about making this part equal to 1, right? So how could I make c squared equal to 1? Well, the easiest way is just to divide by c squared, right? So what I could do is divide both sides by c squared. So what I would have is a squared divided by c squared plus b squared divided by c squared equals, so c squared divided by c squared is 1, right? So we landed at what we wanted, right? So just to point out here, let me just write this in a different color. So when you have like 1 plus 3 divided by 2, let's say this is equal to 1/2 plus 3/2, right? So what you can think about is going from the left side to the right side. That's how we add fractions, right? Those two things are going to be equivalent, right? We add the numerators and keep the same denominator, right? So that's why, you know, going from here to here, you have to take each term in the top and divide it by that denominator, right? So you kind of split it up like that, right? And then something else to kind of refresh. So there's an exponent rule. So if you have a fraction, like let's say we have x divided by y raised to the nth power, right? So this is an exponent rule of a quotient. Then when you do this, you have to apply the exponent to the numerator and denominator, right? So what happens is this becomes x to the n over y to the n, right? So what we're going to use here in a moment is going from the left to the right side, essentially, right? So you'll notice like we have a squared divided by c squared, so notice we have like the same exponent. So we can rewrite that using exponent rules as a divided by c quantity squared. And then we can do the same thing with the b squared over c squared. This would become b divided by c quantity squared equals 1. Right? And the reason why I wanted to do that is so that way I can substitute these a over c and b over c for these trig functions that that I just put in this box. Right? So a divided by c is equal to sine, right? So this becomes sine of theta quantity squared plus, and then b divided by c is cosine. So this would become cosine of theta squared equals 1, right? And then a shorthand way to write this is we'll often write like sine squared theta in this fashion, or cosine squared theta in this fashion, right? And the reason why we'll write it like this is so that way it doesn't get confusing if the square is for the degree measure or for the whole thing, right? So whenever you see like sine squared theta, that means sine theta, the whole expression being squared, right? So, so this is one of the Pythagorean identities, right? So then what we could think about now is trying to make the other parts equal to 1, right? So let me do this one in blue. So let me just write down this Pythagorean theorem that we just had written down, that we just established. Let's say I want to make this part equal to 1. Then what I could do is divide both sides by sine squared theta. Right? So this would become sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equals 1 divided by sine squared theta. Right? So I'll just continue on over here. So sine squared theta divided by sine squared theta is 1, and then plus, and then what I can do using those exponent rules like we had just talked about, I can make this be cosine theta over sine theta quantity squared, right? And then this would be equal to, so if you think about it in this way, 1 is equal to 1 squared, right? So if I put a square here, we still have the same expression. So with that in mind, this would just become 1 divided by sine theta quantity squared, right? So using the same exponent rule with this idea here that I presented here. So then now what we could fill in is cosine theta divided by sine theta was one of the quotient identities that we looked at. That's equal to cotangent, right? So this would be cotangent theta squared, right? 1 divided by sine, that is cosecant. So this would become cosecant of theta squared, right? So this is another Pythagorean identity, right? So far we have 1 Pythagorean identity and 2 Pythagorean identities. Right, so let's try another one. So I think I'm going to run out of room, so I'm going to do it off to the side. So if I start off Let me make this a little thicker. So if I start off with the sine squared theta plus cosine squared theta equals 1 Pythagorean identity. If you remember right, what we just did was made this part equal to 1. So let's make this part, cosine squared theta, equal to 1 to get another one, right? So what would I have to divide by both sides to make this part 1? Would I have to divide by cosine squared theta, right? The same thing. So then this would become sine squared theta divided by cosine squared theta plus cosine squared theta divided by cosine squared theta equals 1 divided by cosine squared theta. Right? So I can rewrite this as sine theta over cosine theta quantity squared, right, using that exponent rule. Cosine squared theta divided by cosine squared theta is 1. And then same rationale as what we did right here, right? I can rewrite this as 1 divided by cosine theta quantity squared. So now we can fill things in. So sine divided by cosine is tangent, so this would be tangent squared theta plus 1 equals, and then 1 divided by cosine, that's secant squared theta, right? So there is the third Pythagorean identity, right? So there are 3 of them. So personally, I only remember the first one, and then I can easily get the other 2 using the work that I did here, right? So I often tell my students, in mathematics, it's really hard to memorize everything, right? So it's important to memorize like these core ideas, and then understand the concepts to how I can come up with the other items, right? All right, so let's see. Now ready for example 7. So example 7, we're given that cosecant of theta equals 5/4 for an acute angle theta. Use the appropriate identities to find the value of cotangent theta, right? So we're given cosecant, and we want to find cotangent. So I need to use an identity that involves them both, right? So the one that involves them both is, I think, the second one that we dealt with, right? Yes, cotangent and cosecant. So we want to use the idea that 1 plus cotangent squared theta equals cosecant squared theta. So I know what cosecant theta is, right? So that's 5/4. So this would be 5/4 squared, right? And then I do not know what these values are. Right? So then now what I can do is solve for cotangent. So I could subtract 1 from both sides. So we get cotangent squared theta equals 5/4 minus 1. And this is 5/4 squared. So I can clean that up. So 5/4 squared would be, 5 squared over 4 squared minus 1, which is 25/16 minus 1, which is, let me switch color, it won't show up on the black. So this would be equal to 25/16 minus 16 over 16, right, to get a common denominator. And then this would equal, so 25 minus 16 is what, 9 divided by 16, and then, so I can't reduce that, right? So then, I can divide, that's what I want to stop at, right? I can't reduce that anymore. So then we would have cotangent squared theta equals 9/16, right, is what we have. So then in order to get cotangent theta by itself, right? We need to take the square root of both sides. So we end up with cotangent of theta equals square root of 9/16, which is equal to radical 9 over radical 16, which equals 3/4, right? Radical 9 is 3, and radical 16 is 4, right? And that would, if you want a decimal, is 0.75. Right? All right, so we're ready for the next part. So we want to look at complementary angles and cofunctions. We see how we're doing on time. So 40 minutes. Okay. All right, so if you remember, complementary angles are angles that have a sum equal to 90 degrees, right? So if you forget that, we can just write that real quick. So two angles are complementary if their sum equals 90 degrees. Right? So if we draw a diagram here, we could let this be A, B, and C. And let's say this angle is theta. Then, if we remember about how the two non-right angles, the two acute angles are related, remember they add up to be 90 degrees. So this angle would be equivalent to 90 degrees minus theta, right? So something to think about is that if we think about sine of theta, that's going to be equal to the opposite over the hypotenuse. So that would be A divided by C, right? But then something kind of interesting is that if I do cosine of the other angle, which would be 90 degrees minus theta, that would be equal to the adjacent side, A, divided by the hypotenuse, which is C. So these guys are equal, right? They're equivalent. So we can kind of look at this phenomena a little more by looking at, tangent of theta and cotangent of 90 minus theta, 90 degrees minus theta, is they're both equal to A divided by B, right? Same rationale, same idea. And secant of theta is equal to cosecant of 90 degrees minus theta, which are both equal to C divided by B, right? So then, to have a statement that we can list here, so if we say let theta be an acute angle and F and G being two trigonometric functions, then F and G are called cofunctions if F of theta equals G of 90 degrees minus theta and G of theta equals F of 90 degrees minus theta. Right, so that's a definition of cofunctions, which is what we want to look at next, which are cofunction identities. So cofunctions of complementary angles are equal is what we'll find, right? So this is just a definition, right, that you could write right here if you wanted. Right? So that's kind of an interesting fact about complementary angles and how sine and cosine, tangent, cotangent, secant, and cosecant are related to one another. So in general, what we can say is that sine of theta equals cosine of 90 degrees minus theta. Also, cosine of theta equals sine of 90 degrees minus theta, right? And then we could also rewrite this, instead of saying in degrees, we could do that in radians. So remember that pi over 2 radians is equal to 90 degrees, right? So I could also say that sine theta equals cosine of pi over 2 minus theta, and also cosine theta equals sine of pi over 2 minus theta, right? So in other words, sine and cosine are cofunctions, right? So next, what we're going to find is that tangent and cotangent are cofunctions. And as you could guess, secant and cosecant are also cofunctions. Right? So we can make similar statements here. So we could say, for example, tangent of theta equals cotangent of 90 degrees minus theta. Also, cotangent of theta equals tangent of 90 degrees minus theta. And then we can make the same statements for radians, right? We could say that tangent of theta equals cotangent of pi over 2 minus theta, and cotangent of theta equals tangent of pi over 2 minus theta, right? And then we can make similar statements for secant and cosecant. So we could say, secant of theta equals cosecant of 90 degrees minus theta. Cosecant of theta equals secant of 90 degrees minus theta. And then lastly, for radians, we could say that secant of theta equals cosecant of pi over 2 minus theta, and cosecant of theta equals secant of pi over 2 minus theta. Right? So just a little tip to help for some of this to make sense is that cosine literally means that it complements sine. Complements sine. Right? So cosine and sine are cofunctions, right? Cotangent means that it complements tangent. Oops. Right? Cosecant literally means that it complements secant. Right? So cosecant complements secant. Cotangent complements tangent. Cosine complements sine. Right? So that might help you remember that relationship. Right? So then example 8. So for each function value, find a cofunction with the same value. So we have that tangent of 22.5 degrees is equal to radical 2 minus 1. So the cofunction of tangent's cotangent. So, tangent of 22.5 degrees would be equal to cotangent of 90 degrees minus 22.5 degrees. Right, so that's just using what we just went over, right? So then this would just be equal to cotangent of, so we take 90 minus 22.5, what's that, 67.5 degrees. So that's going to be equal to radical 2 minus 1, right? So this is what we were after, right? So that, so using the cofunction, we found the same value, right? So then similarly, if I want to look at secant of pi over 3, this would be equal to, so since this is, this is in radians, there's no degree symbol, then this would be equal to, cosecant of pi over 2 minus pi over 3, right? So we need to get common denominators, so this would be cosecant of, so we could get common denominator 6, so that'd be what, 3 pi over 6 minus 2 pi over 6, which is equal to cosecant of pi over 6. And that would all be equal to 2, right? So right there's what we were after, right? So cosecant of pi over 6 is going to have the same value, right? All right, so then objective 5 is helping us with using a calculator to approximate trigonometric functions, right? So it's often the case that we cannot find exact values of trig functions analytically like we've tried to do using 30, 60, 90, 45, 45, 90 triangle. So what we can do if we can't find this exact value is we can get an approximation by using a calculator, right? So parts A, C, and D are pretty straightforward, especially A and C, right? So let's maybe do A and C first, and then we'll do the next easiest one, which is D, and then we can work through part B together, right? So part B, notice that it has degrees and minutes there. All right, so let me pull up my graphing calculator. All right, so very first thing that you want to be comfortable with on your graphing calculator is what mode you're in, right? Degrees or radians, right? So if you hit the mode button, you'll notice here where it says radian and degree. So you just want to always get in the habit of checking that because that makes a big difference, right? So part A, we're in degrees, so I'll leave it in degree mode. And then I can just type in sine of 46.3, right? Hit enter, and we get this value, right? And we want to round to 4 decimal places. So this would round to be approximately equal to, oops, let me, 0.7230. Right? So then maybe the next easiest one is part C. But notice with part C, it doesn't have it, there's no degree symbol there, right? So that implies that we're in radians. So let's go to mode, switch this to radians. So then if I hit tangent of 1.4, we can get that this is approximately equal to, so 4 decimal places, that would be 5.7979. Right? So then cotangent of pi over 8 is equal to 1 divided by tangent of pi over 8. Right? So notice I don't have a cotangent button on my calculator. I have sine, cosine, and tangent. So that's why we want to rewrite that using the reciprocal identity. Right? So I can type this in my calculator. 1 divided by tangent of pi over 8. And then, so this is approximately equal to 2.4142, right? And then, so the last one, part B, really what we need to do here is just convert 11 degrees in 8 minutes. Just convert that into blank degrees, right? So remember, there are 60 minutes in a degree. So this would be 11 and 8/60ths of a degree, right? So essentially, this would be equal to cosecant of 11 plus 8/60ths degrees, right? So we could just type this in my calculator. Also, we don't have a cosecant. So if you wanted, first, we could just type in 11 plus 8 divided by 60. And I can hit math and turn my answer to a fraction. And my calculator is going to convert that into a fraction for me. So this is equivalent to cosecant of 167/15 degrees, right? So then this would be equal to 1 divided by sine of 167/15 degrees. Right, so then now I can finally get a decimal approximation. So I have a sine button in my calculator. So I just need to do 1 divided by sine. Wait, we got to make sure we're in degrees. So if I hit mode, we're still in radians. So I need to hit that, turn it into degrees. So then I have 1 divided by sine of 167 divided by 15. Whoops, 7 divided by 15. And we get approximately 5.1789. Right? So not too terribly difficult, right? So it's just important to remember the calculator mode, right? That's going to come up a lot as well. Right. All right, so we're ready for the last objective in this section, which are using trigonometric functions and some applications. So I have three examples for us to work through. Right. So example 10. Suppose that a farm worker determines that the distance along the ground from her position to the base of a palm tree is 16 feet. She measures the angle of elevation from an eye level of 5 feet to the top of the tree as 45.9 degrees. Is the tall enough to harvest? Is it at least 20 feet tall? Right? So, with word problems or really anything, it's really important to, understand the problem first before you start trying to solve, right? If you don't understand what's going on, it's not going to be helpful just to try to plug things in and just hope for the best, right? So personally, I'm a very visual learner, so I always like to start by trying to draw a picture. And, some tactics that I'll do is, maybe start to draw a picture and then fill things in as we go. Let's see. So determine the distance along the ground from our position to the base of the palm tree is 16 feet, right? So in other words, let's think this is the palm tree. Oops. Right, so this is the tree, right? It's not a very good tree, but hopefully you get the idea. It looks more like a carrot, I guess, but so this is the tree. Over here is the worker, and this is the eye view, right? Maybe there's the ground. So I'll just draw this in. This is the tree. So what we know is that from her position to the base of the tree is 16 feet, right? So in other words, this distance here is 16 feet. What we also know is saying that eye level is 5 feet of the person. So what that tells me is, this distance here is 5 feet, right? From the ground to the eye level of the worker. And then the measure of elevation, angle of elevation, is 45.9 degrees. So that would be this measurement here. So that's 45.9 degrees. And then, so what we're trying to find is the tree tall enough to harvest? We want to know, is it at least 20 feet tall, right? So what I would do is label this be x feet, right? So that part of the tree, right? So in other words, the height of the palm tree equals x plus 5, and that would be in feet, right? So the question is this greater than or equal to 20 feet, right? This is the question that we're trying to answer. If the answer is yes, then we can harvest it. If it's no, we can't harvest, right? So in other words, kind of like a decision tree. If the answer is yes, then we harvest. If the answer comes out to be no, then we don't harvest. Right, so we want to think about, how can we work through this, right? So if I just draw the triangle without the heights and things, right? This would be x. This is 16, and we know this to be 45.9 degrees, right? Then we can try to think through, what trigonometric function involves the opposite and adjacent sides of an angle, right? Because 45.9 degrees, we have that angle. X is the opposite, and 16 is the adjacent, right? Well, that would be, tangent or cotangent. And I recommend, sine, cosine, and tangent are going to be the easiest to use because we have those buttons on our calculator, right? It's just maybe a little more convenient. So I would just go with tangent. So what we're trying to do is figure out what x is, right? Because if I know what x is, then I can add 5 to it and determine the height of the tree, the palm tree. So really our goal right now is to find x, right? So tangent of 45.9 degrees would be equal to the opposite, which is x, divided by the adjacent, which is 16, right? Just using SOHCAHTOA. So if I multiply both sides by 16, then what we end up with, so these cancel, we get x equals 16 times tangent of 45.9 degrees, right? That's an exact answer, right? So then the height of the tree is going to be equal to 16 tangent of 45.9 degrees. Oops, that's a 4. 45. 45.9 degrees plus 5, and that answers in feet, right? So if I take, I want to make sure my mode, in degrees. So we would take 16 times tangent of 45.9 plus 5, and we get roughly 21.5, right? So this is approximately 21.5 feet, which is greater than or equal to 20 feet, right? So we're good. So the answer, the conclusion would be yes, right? So we could say, yes, the tree is tall enough to harvest, right? So then next one is example 11. So what we have in this case is we have a 15-foot ladder leaning against a wall at an angle of 62 degrees with the ground. How high up the wall will the ladder reach? Down to the nearest tenth of a foot, right? So this one I think is maybe even a little easier to grasp, right? It's not as many details. So we can think about this being like the floor. This is the wall. And this is my ladder, right? The ladder is 15 feet in length. This angle is 62 degrees, right? We're told it makes that with the ground, right? So I guess instead of saying floor, we could say ground, just to be consistent. And then what we're trying to find is how high up the wall will the ladder reach. So we're trying to find this distance, so we could, I don't know, maybe just call it h for height, right? Height of the ladder. That's what we're trying to find. So what we have is we have this angle, and we are dealing with the opposite side and the hypotenuse. So which trig function deals with opposite and hypotenuse? Well, that's sine, right? So we can make a statement. We could say that sine of 62 degrees is equal to h divided by 15, right? So then we could multiply both sides. Whoops, sorry about that. Multiply both sides by 15 and get that h equals 15 times sine of 62 degrees, right? And that's in feet. That's my exact answer. And I'm trying to find an approximate round to the nearest tenth of a foot, so that's 1 decimal space. So I know we're already in degrees, so we do 15 times sine of 62, and we get roughly 13.2 feet. Right? All right. So one more example left, right? So with this one, we're told an airplane traveling at 400 miles per hour at a cruising altitude of 6.6 miles begins its descent. If the angle of descent is 2 degrees from the horizontal, determine the new altitude after 15 minutes. Round to the nearest tenth of a mile. Right? So let's try to draw this a little bit. So basically, we have an airplane traveling, this way, and then suddenly it's starting to make its descent. So it's gonna make like this right triangle. Oops. Right, because we're suddenly going downward here with the airplane. Let's see, we're told that the angle of descent is 2 degrees from the horizontal, so the horizontal is like the ground, right? So that tells me this is 2 degrees. We're told that the altitude of the plane as it's beginning its descent is 6.6 miles, so that would be this distance. And what we're trying to find is the new altitude after 15 minutes, right? So kind of, and we know the speed of the airplane, right? So basically the way I'm imagining this, and maybe it would help if, let me kind of zoom in and make this a little bigger, is after, the plane's going to keep going, and then after 15 minutes, what we want to do is figure out the height of the plane, right? So in other words, I want to find this h value, right? That's what we're trying to figure out, right? Um, so what would be helpful is if I knew, so let me just put this in yellow, if I knew this whole distance, right? If I knew that whole distance, then what I could do is subtract off the distance that I would go in 15 minutes, and then we could figure out this distance to try to figure out h then, right? Is kind of my line of thinking, right? So to be able to do this, what we need to know is a common formula that's used in physics and mathematics, which is distance equals rate times time, right? All right, so let me maybe redraw this a little bit. Let me make this a little cleaner. Right, so this is 2 degrees. And then essentially what we have going on is a similar triangle inside. So this is 6.6 miles. Let's let this be y. Let's let this whole distance side be x, and let's let this part be z. Right, so I'm just trying to label those parts that I pointed out before. So, really the goal is to find z, right? So the answer equals z miles, right? Because we want to find the new height. So z represents the new height of the plane after 15 minutes. So using distance equals rate times time, we know that r equals 400 miles per hour, and time is 15 minutes, right? But we want to have this in terms of the same units. So 15 minutes is 15 over 60 hours, right? So my distance that I'm traveling in 15 minutes would be equal to 400 miles per hour times 15 over 60 hours, which would get me to, so if I take 400, excuse me, hang on. So if I take 400 times 15 divided by 60, we get 100. So this would be 100 miles. Right? So essentially what I found is that this part here is 100 miles. Right? So by using this diagram, y is going to be equal to x minus 100 miles. Right? So, and then if I figure out what y is, I can figure out what z is by using a trig function. Right? So to find x, I also need to use a trig function. So we're going to use 2 trig functions. Right? So we have this angle. So now I'm thinking about x and 6.6 miles. Right? I'm thinking about like the big triangle. So that deals with the opposite and the hypotenuse of 2 degrees. So that would mean I would use sine, right? So sine of 2 degrees is equal to 6.6 divided by x. So if I multiply both sides by x, those cancel. I get x times sine of 2 degrees equals 6.6. And then to get x by itself, I could divide both sides by 2 degrees, sine of 2 degrees. So that leaves me with x equals 6.6 divided by sine of 2 degrees. Right? So y is equal to 6.6 divided by sine of 2 degrees minus 100 miles. Right? So I'm going to leave it like that because something that's important is if we use an approximated answer to get another answer, we're going to have rounding error. Right? So I want to leave it as exact as possible. So I'm going to leave it in terms of this. Right? And sure, we might be able to make this a little simpler, maybe one expression, but it's not really necessary. Right? We don't need to do that. So then the next thing I'm going to do, let me change my color, is right now what I'm focusing in on, maybe I'll use red, is the y, the z, and the 2 degrees. Right? So that the smaller triangle, so I'm going to use a trig function. So that's dealing with the opposite and hypotenuse again still, so that's still sine. Right? So sine of 2 degrees is equal to, maybe let me use green. It's a lot more different than black. That looks somewhat similar to me. So sine of 2 degrees would be equal to z divided by y. Right? And we already know what y is. So we would have sine of 2 degrees equals z divided by 6.6 divided by sine of 2 degrees minus 100. Right? So then, let me make this a little smaller print. So then what I could do is multiply both sides by the denominator, 6.6 divided by sine of 2 degrees minus 100. And then multiply that same thing over here. So 6.6 divided by sine 2 degrees. Oops. Minus 100. So what that gives me is, so these will cancel out. We get z equals sine of 2 degrees times 6.6 divided by sine of 2 degrees minus 100. Right? So we can just put this into the calculator and get an approximation. So sine of 2 degrees times 6.6 divided by sine of 2 degrees minus 100 gives me approximately 3.1 miles. Right? So that's the answer that we wanted. Right? So this one we had to use 2 trigonometric functions. Right? All right, so that finishes up section 5.2. Be sure to let me know if you have questions. I'll be glad to help. Thanks.